So cue the dramatic intro. It mentioned hacking up there, but the only hacking we're going to do today is in the dungeon. So quick show of hands from the audience. Who here has played Dungeons & Dragons? That's about half of you. I'm disappointed. Which version? Do you play 5th edition or Pathfinder? Just shout it out. Everyone's playing 5th edition. Pathfinder, excellent. I actually am a big fan of Savage Worlds, which is a game I really like. But anyhow, welcome to my talk, Dungeons, Dragons, and Graph Databases. Quick point of clarification, and this is not intended to scare you off if you think this is something it's not, but we're going to talk about graph databases. Graph databases and GraphQL are not the same thing. GraphQL is a query language that is used kind of like REST to query services through over HTTP. Graph databases is a way of storing data using graphs. We're going to go into detail on what that means and stuff like that, but graph databases are their own thing. They pair very nicely with GraphQL, but they are their own thing. So, welcome everyone. My name is Guy Royse. I'm a developer advocate at Redis. I'm here to say buy more Redis. This graph talk isn't, this is a graph talk about the graph capabilities of Redis. I'm not really pushing them. It's a thing I'm using. You can use any graph database to do, well, many graph databases to do what I'm going to show you today. For those of you who are still on Twitter, give me a follow at Guy Royse. I appreciate that. The thing on this screen here that matters the most is the GitHub URL right here. Let me get to it. There we go. That's my GitHub. I have a repo out there that has all my slides and the code that I'm going to demo and just a bunch of stuff to check out there. And you can get a hold of me at guy.dev. Guy@guy.dev is actually my email address. So I'm a developer advocate at Redis, but I'm also, as you might have guessed, a player of Dungeons & Dragons. And so I thought it might be worthwhile to share my character sheet. And so you see here that I'm neutral good. I thought that was a reasonable alignment. I think that's probably most people, honestly. The closest thing I could find to developer advocate in the player's handbook was bard, so I guess I'm a bard. And I'm clearly a dwarf. And there's in my armor class and my hit points. Of note on my stats here, I've shared my stats. I'm a little hardier than you might think with a constitution of 12, but I've got a little extra bulk that slows me down, and so I've only got a dexterity of 8. And down here at the bottom, you see that my intelligence and wisdom are both 8s, and my charisma is 16. And that tells you everything you need to know about this talk. It's going to be all sizzle, no steak. And as a player of Dungeons & Dragons, I've got a problem. And that problem is that I need to figure out how to maximize my character. I need to level up. I need a power game. And I want to level up my character as fast as I can so I can be powerful and capable in the game. And in order to do that, I need to go to the dungeon and find the rooms in the dungeon that are most suited for me gaining experience. So I got to find rooms with the best monsters with the highest or most appropriate level of experience so that I can defeat them and take their experience. And I need to find the rooms that have the best treasure so that I can buy better gear and power up my character as well. And this is a problem that many of us gamers have. It's just sort of fundamental to the game. And I thought, well, I'm a developer advocate. I'm a player of D&D, but I'm also just a developer. And so I could solve this with a database, and I could make a database of my dungeon. And then I could query that database and then say, well, which room should I go to next? Give me a list of rooms in priority order that I need to go to in the dungeon to get the most out of my gaming time at the table. And of course, there's a couple ways that I could model this in a database. Option 1, sort of the default that a lot of times you go to, is a relational database. How many here have used a relational database in your career? There should be like everyone, right? SQL or SQL, depending on how you say it, is the first way, not the first, but it's the only programming language that I learned in college, and it's arguable whether SQL is a programming language. It's declarative. But it's the only language that I learned in college that I still use. They didn't have JavaScript when I was in college. I learned a lot of COBOL in college. I still use C occasionally. That's not completely fair, but yeah, that's the one I used. And so my first thought was, let's build a relational database with the tables and the columns and the relationships and the foreign keys. But I could also model this data using a graph database. And so this is really going to be the theme of the talk, is I'm going to show this is how you would solve this problem with a relational database, and this is how you would solve this problem with a graph database. And a graph database has nodes and edges and labels and relationships and all this great stuff. And so this begs the question, of course, what's a graph database? And it's actually not the first question we need to answer. The first question we need to answer is, what's a graph? Now, many of you have probably taken math courses and learned about graph theory. And for you, this will be a little bit of review. But as always, I don't want to leave anyone behind. And so I'm going to start with some fundamentals and sort of go through graph theory in like 5 or 10 minutes. A graph is a mathematical representation of, well, stuff that consists of nodes or points or vertices and edges or relationships or connections that connect them together. They can be used to model things like this 20-sided die. This 20-sided die is a graph. It's a Platonic solid. And you have a vertex, which is the point on that 20-sided die. And you have an edge, which is, well, the edge of that 20-sided die. And so you can represent things like Platonic solids with graphs, but you can also represent more complex structures, more abstract things. It's not just about geometry. For example, you could represent all of the people in a family with a graph. Or you could represent all the people on Twitter in a graph. You could model contact tracing. That seems relevant recently, with a graph showing who has come into contact with whom. The simplest graph is a null graph. Isn't it exciting? Yeah, no, it's not. I'm a JavaScript developer, so actually I call this an undefined graph. I was hoping that joke was funny. Mathematicians argue about whether a null graph is actually a graph or not, and I just kind of don't care, because there's nothing to see here. It's not that interesting. Graphs are interesting when there's content in them. And so let's add some nodes to our graph. Now we have a bunch of nodes, and here we got nodes A through G, and they're just out there. They're just points sort of floating in space. They're not related to each other. There's no connections between them, but we know they exist. And you could kind of think of this as a set. This graph represents the set of nodes. We don't have any information about the nodes, and we don't have any relationships about the nodes, but we know they exist. To make this a little more graphy, and it's something you might think of as a graph, we can add some relationships between these nodes. And so now we've got nodes B and F here that are connected together, best friends forever. You've got node E that clearly is all by its lonesome. And then you've got the main part of the graph with nodes D, A, C, and G, which are in a, there's a little more relationship there. So now we're starting to get some information. We don't know what these things are. We don't know what the relationships mean, but we have some sense of this is connected to this. And so it's coming in, you can see how you could put information on this and it becomes a useful structure. We can talk about some of these parts of these graphs based on, well, this is sort of a taxonomy of words we use to talk about graphs. A node on a graph that has no connections is isolated. A chunk of the graph that's not connected to the larger graph is also isolated. And in fact, since this graph isn't, every node is connected to every node, even the big part is technically isolated because it's not connected to the other things. And so we can talk about portions of subgraphs of a graph being isolated or nodes within a graph being isolated. Let's go ahead and connect all the nodes. And when we have a graph that looks like this, where every node has a connection directly or indirectly to another node. So, for example, node D can connect to node E. So I'm pointing at the screen, but that doesn't help you. Node D can connect to node E. And there's some paths that it can follow. They're not directly connected, but there's paths that can follow. This graph kind of graph is referred to as being connected. And so a connected graph is one where every node has a path to any other node. A good example of a connected graph would be the transportation system of Europe. There's roads and rail and everything that connects everything together. There's no isolated portions of the European road system that isn't connected to some other part of it. It's connected. You can also have fully connected graphs. And I don't have a picture of a fully connected graph, so I'm going to show you a subgraph of this here that it shows a fully connected subgraph. A fully connected graph is a graph where every node connects to every other node in the graph. I was at the speaker dinner last night, and it occurred to me, I was thinking about this talk, and we were doing, cheers, salud, I can't remember what you say in Polish. They told me, but I forgot. It's fallen out of my head. But I was thinking about the fact that you have to touch everyone's glass, and everyone has to touch yours. And that represents a fully connected graph where every node has connected to every node. If you've ever seen a network diagram, or a diagram that shows like a bunch of nodes in a network in a circle, and you got a line connecting every single one of them to every single one of them going across the middle, that's a fully connected graph. Every node connects to every node. This particular graph we've been looking at here is undirected. And so what that means is that the connections between the nodes have no direction to them. There's no additional information. We know that node B is connected to node F. It's kind of like being friends on Facebook. Like if you and I are friends, I'm going to pick on you. If you and I are friends on Facebook, then that's an undirected relationship. It's bidirectional. It's just intrinsically goes both ways. If I'm your friend but you're not my friend, that doesn't exist. That doesn't work, right? So an undirected graph represents those sorts of structures. However, you can make directed graphs which provide a little more information, where we have some information about the direction. I always use the word directionality, and I can never think of another word other than direction to explain direction. But where that relationship has a direction. And this is like on Twitter. So on Twitter, I might follow you, but you don't follow me. Or maybe you follow me and I follow you, and then we have directed relationships going both ways. And so this is a little bit of extra information. Another example of a directed relationship that I like to use is a mother and a child. That has a natural direction to it. My mother gave birth to me, not the other way around, and so has a direction. And so directed graphs can represent these sorts of relationships. When we talk about nodes in a graph, we can talk about their degrees. The degree of a node is the number of relationships it has. That can be 0. In the case earlier where E was all by itself, it would have had a degree of 0. Here, node A has a degree of 3 because it has 3 relationships. If the graph is directed, you can have an out degree, which is the number of relationships heading out, and you can have an in degree, which is the number of relationships coming in. And most importantly, anything can connect to anything. There's no real rules about how these things connect. I've been doing this convenient little, flat thing so it looks nice on a slide. But if I tried to draw a graph representing the surface of that die 20 that we looked at earlier, there's no way I could draw that on a flat piece of paper. And so nodes can connect to themselves. They can connect to each other multiple times. They can be bidirectional. You can cross the streams. It's not like Ghostbusters. And so lots of choices. You can run it any way you want. No real rules. So that's graph theory in like 5 minutes. Thank you for attending my TED Talk. Yeah. I'll take the applause, but it's not the time yet. A graph database, then, is when you take this structure and you lay data over top of it. These nodes don't represent just the letters. They're not just there. They represent things. So they represent the rooms and the monsters and the treasure in our dungeon. And we can attach data and labels to them to make that so. So here we've got, for example, a node that is a monster. It's got data associated with it. It's got an ID of 4. It's got a name of Alice the elf. It's got a challenge rating and experience points. And we have a room, and it's got a label of a room. And it has other attributes the room has. A fun fact here, we got Alice the elf and Bob the ogre. Well, it's a fun fact to me anyhow. You probably don't care. But Alice and Bob, we always use them as sort of like the canonical users. It turns out that's my grandparents' names. So my grandmother's name was Alice, and my grandfather's name was Bob. And Alice, my grandmother, was kind of elfin in a way. My grandfather was not an ogre, though. He was a very nice old man. So I grew up with them. They were fantastic. And so we're going to use Alice and Bob here throughout our examples here. Because coincidentally, I put together this talk and then I realized after the 5th time of giving it, it's like, oh, crap, those are my grandparents' names. So now they're the stars of the show. But yeah, so you can lay data on the nodes of the graph, and you can actually lay data on the relationships of the graph as well. And so here we've got rooms that connect to other rooms and rooms that contain monsters and that sort of thing. So graph database is just this graph structure with data laid over top of it. And this lets us build a database worthy of Mordor. A little bit of a summary here and just a couple clarifications. The nodes in the graph tend to represent items. They tend to be nouns. They have labels, one or more. So you could have a node that's a room, but it could also be a chamber. Or you could have a node that is a monster, but it's also like a goblinoid. They have attributes, key value pairs associated with them. And a node, just like in a graph database, can stand alone. So you can just have a node and it's just out there and it's just got data hanging on it. It doesn't have any relationships. Relationships represent the connections between two nodes. A relationship, by definition, is the connection of two nodes. No more, no less. And these relationships have a type, which is a lot like a label, but it has one type. It can't have multiple types. They have a direction. So the room contains a monster, not the monster contains a room. And they also can have attributes on them as well. I find that generally, if you're putting a lot of attributes on your connections, like a distance one makes sense. If you're using a graph database for like pathing and you want to find the shortest path, then you can use that as a weight and say use this one more or use this one less. But if you find yourself putting a ton of data on there, like if you think of, I got a room and there's a door that leads to a room, and then that door is the relationship, you probably don't have a relationship. You have another node, which is a door node, and then the room contains a door, and the door leads to another room. Although I'm not going to model that in this example. And most importantly, a relationship cannot exist without a node, without two nodes. If you delete a node in that relationship, the relationship's gone. It evaporates, it's deleted. So if you delete the node, its relationships go with it. So, what do we got next? I like to say that they can read like a sentence. I mentioned that the nodes tend to be nouns. Well, the relationships tend to be verbs. And so you end up with this nice little transitive sentence. The room contains the monster. And so you've got a room node contains directed a monster. And so I find that if my graphs that I'm building read like sentences, then I'm modeling my problem domain well. So that's the theory behind it all. This is kind of what a graph database is. And there's probably some of you thinking already, this looks kind of fun. Like if you think about if you're like a Java developer and you do a lot of object-oriented stuff and where you have like, say, a policy, and then you've got, covered vehicles on that policy, or you've got a bank, an account, and an owner to that account, you start seeing relationships and say, I could model all sorts of cool stuff with this. And it matches the way I code. So if I have object-oriented programming languages, the object-oriented, the graph kind of maps to that neatly. So I find modeling problem domains in graph really nice. So, but enough theory. Let's go ahead and look at, because we've still got this problem, right? I still don't know which room and which has the best monsters and the best treasure for my dungeon crawl experience to power game my character. And so, how are we going to solve this problem? Are we going to use a relational database, or are we going to use a graph database? Spoiler alert, we're going to use a graph database. But what I'm going to do is I'm going to show how you solve this with a relational database to contrast that to how you would solve it with a graph database. Because we've all used relational databases. It makes for a smoother understanding. And when we talk to a relational database, what's the language we use to talk to one? I mentioned it earlier. We use SQL. Is it SQL or SQL? I say both, and I don't know why. Okay, that's a good distinction that I'm going to ignore. But yeah, so we use SQL to talk to a relational database. And so select star from users where clue greater than 0. By the way, that query always returns 0 users. So what's the equivalent language to talk to a graph database? Well, one language in particular created by the folks at Neo4j is Cypher. And Cypher is sort of like a cross between a query language and ASCII art. I know that's a weird thing to say, right? It's a little odd. But if you look here at this query, we got a match statement, and then we got this long, kind of weird-looking string here. And then we got a return some variables. And this little string here is a matcher, and it looks kind of like a graph. And I'm going to show it here on the next slide. It shows a little bit better. These matching strings, they're kind of designed to look like how we draw our graphs. You draw the nodes as circles, and you draw the relationships as arrows. And so here we've got r:room. That matches a room node and assigns it to the variable r for use later in our query. And we put it in parentheses. Why? Because we draw circles for our nodes. And so it kind of looks like a node. And over here, we've got a m:monster. This matches any node with a label of monster, and then assigns it to a variable m so we can use it later in our query. And here in the middle, we've got the relationship called contains, and it assigns that to a variable c so we can use it again later in our query. And you'll notice that it looks like an arrow, right? I got a dash, and then I got the little label, and then I got a dash and a greater than. So it's showing, it's a little ASCII art representation of the portion of the graph that I want to match. And so the way these work when you use like the match command is it'll go through the entire graph and find anywhere where the room contains a monster structure is matched in that graph, and then you can filter them and get parts of them and query them and do all sorts of stuff. But it's kind of like ASCII art. The first time I saw this, I was struck by how remarkably intuitive it was. Now there's a limitation, of course, because you can only do so many arrows in a line. And so if you want to create like a node, a room that contains a monster and contains a treasure, you can do that because you just have arrows going both directions. But if you want a room that contains a monster and a treasure and a trap, then that's harder to represent. There are ways to do it with Cypher. We're not going to get into them, but you can basically do nested matchings. So this is the basics of Cypher. This is the key idea in Cypher is these matching patterns. So let's do a compare and contrast with some CRUD operations for graph databases versus SQL databases, relational databases. And so here we've got a rooms table and some rooms nodes. And we want to do a create first, because we've got to create something before we can query it. So we're going to do create, read, update, and delete in that order. And so to create a room, for starters, you have to have a schema. And so there's a table that exists, and we know it has an ID and it's numeric, and then we know it has a name and it's a string. And to then insert something into that table, we use an insert statement. Insert into rooms, the columns we care about, the values for those columns. And so here we're inserting the statue room. So we've done this a million times. How do we do this with Cypher? Well, we use a create command, and we give it a pattern of the thing that we want it to create. So we want it to create a node. See the little the parentheses there? Give it a label of room. So that :room says give it a label of room, and then assign it to a variable r so that we can use it later in the query. And then we use the set command and set some properties on that newly created node. And that will create a node with those two properties. A big difference to what's happening here is that in the relational database, you've got a schema, you've got columns defined, you've got a table defined, you know what the structure needs to be. In the graph database, there is no structure. And so I can put any label that I want on a node, and I can put any properties on it that I want. And so I've added ID and room, or ID and name here, but I could easily change my mind later and add more. So one has a hard schema, one does not. There's pros and cons to both those approaches. That's just the approach that these types of graph databases use, is they don't have a hardly defined schema. So we've created a room, let's query it. So in SQL, select ID and name from rooms where room ID is equal to 1. Easy peasy. How do we do this with a graph database using Cypher? Well, we use the match command. And so match is sort of like select. And so we're saying match against the graph, look through every node in the graph, look through the entire graph and find that pattern where you've got a node with a label of room. Assign it to the variable r. And then filter it using a where clause and say, well, just give me the one where the ID is 1. This is conceptually what it's doing. Behind the scenes, it's optimizing this. It's not actually just pulling every node and then checking. And then we can return that node. And then this gives us the node and the data on that node. And there's something interesting here, and we're going to see it in the next slide, because when we go to update a room, we're going to use the same syntax, but instead of returning it, we're going to do something different. So when it comes time to update a room, my grandma Alice is going to, it's no longer a statue room. She's got some more statues now, so it's a statue hall. And so we want to update the name. So we update the room, set the name to what we want it to be, give it a where clause to filter appropriately, as we do with SQL. To do this in graph, it's very, very similar to what we just did for reading. We're going to match a pattern. We're going to match a room where ID is 1. So match where. But instead of returning it now, we're going to set properties on it. Now here we're going to replace the name from statue room to statue hall. Again, this is schemaless. So if we wanted to add new properties that don't exist, we could. We could say, set r.trapped to true. And then deleting, everyone's favorite operation. Someone told me one time that deletion is 100% file compression. A couple of you laughed. It's true. It's a little lossy, though. So if we want to delete a room, we're going to delete the statue room now. So we delete from room where ID equals 1. Make sure you put that where clause on there. You're going to have a bad day. Who's never done that before? Nobody raises their hand, right? Thankfully, it was in test, not in prod. But yeah, so delete. So how do we delete in Cypher? Well, we match, we where, and then instead of returning, instead of setting, we delete. And then we delete that node instead. And so those are basic CRUD operations with Cypher. A note on the syntax I've been using. I've been using a syntax that's very much paralleling what's happening with the SQL, but you can abbreviate this a little bit. So I've been using this syntax where I'm saying match where. But you can sort of condense that down and include the attributes on the node as part of your matching pattern. So instead of saying match all the rooms where it has properties, I can say match me a room with properties. And so you just put curly braces on it, and you do field name and colon value. The syntax is exactly the same things that you would use in JavaScript code for strings and numbers and booleans and stuff. And so this is can be a little bit helpful. And you can do that when you call create as well. So here we're creating a room and setting properties, but we can create a room and provide the properties. And you'll notice that here where I'm creating the room, on this bottom one, I don't assign it to the variable r. And that's because I don't need to use that variable anymore. So I'm able to not do that. And so here we're creating monsters the same way we created rooms, but I'm using this new syntax down here on the right without assigning to a variable. And here I'm creating treasure, and it's the same syntax here again, but I'm mixing them together. So here I'm creating t:treasure, giving it a couple of properties in the create, but then I'm setting another property after that. And so you can mix and match these. And so here's our relational database so far. We have 3 tables, no relationships. And they've got some rows in them. We've got rooms, monsters, and treasures. Our graph so far is just a bunch of points hanging out there in space. They have labels, so we know what type they are. We know that they're rooms, or we know that they're monsters, or we know that they're treasure. And they've got the properties that we've given them. But how do we connect these things together? How do I put a monster in a room? Well, to do that with a relational database, the first thing you've got to do is you've got to alter your table. So you've got to add a foreign key to your monsters database, or your monster table, so that it has the room ID in it. And then you need to update that table to set the room to what room that monster is now in. And as the monster moves around, you would constantly be issuing updates. How do I put a monster in a room with a graph using Cypher? Well, what we'll do is we can do multiple matches. So here we're matching all the room, signed at the variable R, where the ID is 1. And we're matching a monster, signed at the variable M, where the ID is 4. And then we create a relationship by referencing those two variables. So here on the bottom, we've got, right there, we've got our room, right there, we've got our monster, and then it'll create, in this create command, that relationship, referencing those existing nodes. And so now we put a monster in a room. So that's how you do that. Same thing for treasure. I couldn't not do them all. I'm a little bit of a completionist. Same way for putting a treasure in a room. And so now that we've put monsters in rooms with a relational database, we've got a very classic looking structure here. We've got a room table, and there's one-to-many relationships to monsters and one-to-many relationships to treasures. Our relational database has little isolated pockets. Each room is a little isolated subgraph. The room has a monster, room has a treasure, room has a monster and a treasure. And with what we have so far, we can do some interesting queries. For example, it's Munchkin time. Let's find rooms with good monsters, rooms with good treasures. So if I want to find the rooms that have the best XP, the biggest monster where I can get the most XP, I can do a join. We've done this in SQL before as well, where I select from the columns I care about from a couple different tables, and I join them together where that room ID is equal to the ID on the room table, where that monster's foreign key, or the foreign key to the room in the monster table, matches the room itself. And then we just order it descending, and then this will give me a list of all the monsters with the highest XP to the lowest XP. How will I do that with a graph database using Cypher? Well, we can match a more complex pattern. I've been showing matchings. At the very beginning, I showed a matching with this pattern, and then I was showing simpler ones. But here we're going to say match everywhere in the graph that has a room that contains a monster. Wherever that pattern exists in the graph, return it to me. And if you've got like one room with 2 monsters in it, then you're going to get 2 results. If you've got a room with no monsters in it, you're going to get no results. And then we return the columns that we care about, the attributes on those nodes we care about, and then we order it by the experience points descending. If we want to get all the gold, it's a very similar process. We're here ordering by descending on the biggest treasure. Again, a little bit of the completionist. So far, so good. But so what? We haven't done anything with a graph database that you can't do with a relational database. Why should I care about graph databases? Well, where graph databases start getting really interesting is when you start connecting nodes with the same labels together, when you connect rooms together. Because the way you do this in a relational database is kind of clunky, but the way you do it in graph is very elegant. Let's look at an example here. So if we want to create rooms connected to rooms in a relational database, how are we going to do that? Well, we need to create a new table that represents those connections between the rooms. This is basically a table that is the graph of all the nodes that are the rooms. And so that table's got an ID of one room and the ID of another room, and shows that direction, that connection that you can make. So we create that table, and then we start inserting rows into it. To put connect a room together in graph using Cypher, it's exactly like putting putting a monster in a room or putting a treasure in a room, but instead of creating a contains relationship, you're creating a leads to relationship. And so here we've got a room leads to another room. We match the first room, we match the second room, and we create a relationship between them. It's exactly the same pattern. And so a graph database doesn't see this as a different kind of relationship. I think it's funny in a way that graph databases are actually more relational than relational databases. It's like, it's in the name, come on. But this is really easy to do. It's easy to model. And so when we look at our relational database now, it's kind of complicated. Because we've got this big mapping table up there on the top right. It's a little messy, and querying this is kind of hard. Like if you want to find a path through the dungeon with a relational database, Well, how do you do that? Who here likes recursive CTEs? Like, maybe one person raised their hand. They're a big pain in the butt. I mean, they're powerful. They're very powerful, but they're hard to think about. Our graph database, on the other hand, is, well, it looks really natural. It kind of looks like what it is. We can see that the rooms are connected in a certain way. We can see that we got, like, up top here, this room here leads back to itself. It's got a little exit that just loops around. And you see that, like, this room here and this room here have a bidirectional connection, but then we have a one-way connection in other places. It looks like the dungeon that we're thinking. It maps to how we think about our dungeon. And so with this kind of structure, I'm going to show you how to do the queries for graph. I'm not going to show you how to do the queries for SQL because we got 15 minutes left. B, I just don't want to go that deep into SQL. So we're going to go in and query some interesting things now that we have rooms that are pathed together, that are connected together. And one of the things that are required to sort of understand how that query works is the syntax here. This is a matcher that says rooms that lead to rooms, and so this matches a room node, and this matches a room node. But that star there means something special. And that means match multiple leads to relationships. So match a room that leads to a room, but also a room that leads to a room that leads to a room, or a room that leads to 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 a room. And so this lets you match much more interesting patterns. So it lets you match all the paths in a graph that connect a room to a room. You can imagine that might be an expensive query. It might be a circular query. The database figures out the circular queries. It doesn't crash it. Don't worry. But this lets you match arbitrarily long relationships. There's a variation of it that lets you box it. And so I want nothing further than 3 nodes away, nothing closer than 1 node away. And so you can say, give me all the relationships in a radius, in essence, or in a donut. I don't want anything near me, but I want things that are further away from me. And so we can do queries like finding the nearby rooms. So here we're matching a room with an ID of 1. Presumably we're in room 1. And we want to find rooms that are 1 or 2 hops away. Say we're in a room in a dungeon and we want to say, well, we just finished this room. What are some interesting rooms that are nearby? What are my choices? Where can I go? This will return all those rooms that are 2 hops away. If you were using this with, say, social media, this would be a query on Facebook that would give me my friends and all of their friends. Or more accurately, the path from my friend to all of my friends and all of their friends. You can use this to get the nearby room with the most gold. So here we're doing that same matching where we have a room that leads to a room 1 or 2 away, but we're adding a contains treasure on the destination room. And so now if that room doesn't contain treasure, it won't match. And so we could use this query to find what room we want to go to next to get the treasure. So we're in here, we got the treasure. What's the next room nearby that has the most treasure? We could do this to find the longest path in the dungeon so that we could hit every single room. And to do this, we got another new piece of syntax here where we match a pattern right here, rooms that lead to rooms star, but we capture that pattern, all of those paths that are matched, and assign it to the variable p. And then we can return attributes off of that path. Here we can return all the nodes by calling a little nodes function. We can get the length of that path. And in this case, we're ordering that by the length descending, so the longest path is the top, and then we return that path. And now we find the longest path through the dungeon. This is a very slow-running query. We can find the room with the biggest treasure. So here we're using some more syntax where we're saying match all the rooms that have a label of treasure, and then for all of those, get the max gold piece value of all of those treasures. This is kind of like a group by query in SQL. And we're assigning that to a little variable that we can use later. And then we find rooms that contain treasure where the treasure is equal in value to that. And then we can then return information about that room and the treasure therein. And of course, you can combine all these together and get the path to the room with the biggest gold by matching the treasure, assigning to a variable, get the max treasure, and then getting a destination ID, and then getting the path to that room, and then ordering it, ascending so you get the shortest path. So it gives you the shortest path. And so this is a dense query. I don't expect you to understand it. The goal here is to show you the kinds of interesting queries you can do with a relational or with graph databases. And there's actually, this is the shortest path algorithm, so there is actually a little function down here that's more performant that you can call called shortest path, and that will do the same thing, but like an order of magnitude faster. So that was a whirlwind introduction to Cypher. Let's see this in reality. Let's see this actually do real stuff. I've got a JavaScript application because that's how I live my life. And we're going to go over and take a look at it. We're not going to look at the code too much. I just want you to see that it exists. I've written a whole bunch of code to create random dungeons. And I'm going to shove it into Redis graph. And so is that font big enough? This screen's huge. That's a stupid question. Let's go ahead and run it here. I've got a little server.js. And the code here is kind of fun. I open my graph database, and I call dungeon.generate. And then here it generates a random number of entrances and exits and rooms and stuff. And I've got like a dungeon node, and then the dungeon has an entrance and an exit. And then it's got rooms that are connected together and monsters and treasure. So it's similar to what we've been talking about here. And I'm going to go ahead and run this. I'm going to do npm start, npm start. And this is going to generate a random dungeon. And we just did it. You want to see me do it again? There we go. Hooray, all right? So that's all fine and dandy, but okay, so what, right? Well, we can query this as well. I've written a little demo JavaScript script here, which kind of shows how to query this. And just to show that this is doing something, we're going to do match d:dungeon and return the name of that dungeon. And let's comment out that line there. And if I do npm run demo, then it queries it, and then it returns this. Let's do this. -s pipe jq, just a pretty print. So you see here, I've queried the dungeon. I get my headers and my data. I've got a d.name, and the name of the dungeon is the Shattered Fortress of Gulvenvra. Let's generate another one, just to show you that this is actually generating dungeons. Now we've got the Forlorn Caves of, Lur's Kulk. Let's go with another name. Let's go with one more here. Here we have the Forgotten Caves of Rizkas. So these are just randomly generated names and everything. I never know what I'm going to get. And you can do some of the interesting queries here. All the queries that I showed you here I actually have in here. So like, let's get a little table here of all the rooms that contain anything. This is one of the things I think is kind of neat about graph here. I'm saying room contains n. So that would be monsters or treasure, just any contains relationship. So let's go ahead and run that one. And so we get, it looks like there's a lot of stuff in the Vile Barracks. There's Dolgan the Gorgon. There's a -3 cursed crossbow. Wow, he's going to be easy to defeat. And a fine warhammer, and a -2 cursed pike. Who's rolling up these tables? And just to show you the shortest path query that we had earlier here. So this is that long version of finding the path to the gold. And when I run it here, the query timed out. See, it timed out. So this query is long running. That's sort of the point, really. So let's go ahead and use the shortest path algorithm instead, and it shouldn't time out. There we go. And it returned it in 4.5 milliseconds, which is honestly pretty fast, given what it's doing. Because it's literally going through and matching every room that contains a treasure. It's finding all of these paths and then picking the shortest one. So, how are we doing on time? I've got a cool new view that shows me on the camera here, but I don't know how much time I have left now. So that's pretty much the demo. I think we're almost out of time, so we'll go ahead and go back to the slides. All that code's out on GitHub if you want to check it out yourself. I'm using Redis Graph. You can use this code. The code I wrote will work with Redis Graph. It won't work with Neo4j, but you could certainly make something similar with Neo4j. So, practical applications. So obviously this is a fun and sort of silly application, but on the other hand, it's like, no, I could totally write a game with this, right? So it kind of works. Well, some practical applications include social networks. I've mentioned Twitter and Facebook a couple times, but the types of queries you can do on a graph database are great for find like the density of relationships. So if you find all the people that have lots of relationships to people that are my friends, you can do those sorts of queries. And so social networks are a very natural use case for graph databases. Genealogy, which is arguably social networks extruded out over time. You know, if you like researching your ancestry, you could use a graph database to do that. Transportation networks are logical graphs. If you think about the nodes being the intersections and the bus stops and the train stations and the platforms, and then the relationships being the time it takes, having a value of the time it takes to go on that particular route based on traffic load, then you could query those and find the shortest path weighted through a transportation network. Your phone is probably doing this when you get directions. Logistics, this is great for, let's say you have a problem with contaminated spinach. This happened in the US a few years ago. You can have a graph database that represents the farmers and the trucks and the warehouses and the packing facilities and the stores, and then people who buy the contaminated thing and get sick, they know what store they bought it at, and then you can use that graph and query which farms it might have come from and track down the source of contamination. And I mentioned contact tracing as well. So that's pretty much my talk. I've been at Redis for 1-4 - years. We've got a Discord server at discord.gg/Redis where you can ask questions about Redis, including Redis Graph. We've got a nice little client called Redis Insight, which I didn't demo in this talk, but Redis Insight is fantastic. It's what I almost always use when I'm working with Redis, and unless I'm doing like shell scripting stuff. And there's a URL to get it there, but you can also just get it in the App Store for your Mac, or you can get it in the Windows Store for Windows. So you don't even have to go outside of your ecosystems. And we got free courses at Redis, university.redis.com, so if you want to learn more about Redis, go sign up there, take a free course, learn about streaming, or learn about probabilistic data structures, or just do the Redis 101 if you're new to Redis. So there's the link to my slides if you want to scan it. Those who were in my talk yesterday know the joke I'm going to make, but I'm going to make it again anyhow. You can trust this QR code. It will never give you up, nor will it let you down. And that's pretty much what I've got. I've never actually rickrolled an audience. I can't bring myself to do it. I'm thinking about building a little rickrolling app where it takes you to the site but also shows you the video, just so that I can get the best of both worlds. And that's what I got. So my name's Guy Royse. Thanks a lot.